Today I'd like to talk a little bit about permutations, combinations, and the fundamental law of counting. But let me start by reminding you of something we've already discussed earlier. For a classical probability, given some event A, that the probability of A occurring is the following fraction, the number of ways that that event can occur, divided by the total number of possible outcomes as defined in the well-defined random procedure. Okay, this fraction is very important to understand. Now, in most of the examples we had done up to this time, finding the total number of outcomes was pretty straightforward, and finding the number of ways that A could occur was pretty easy too. Usually it was just one way. But now we're going to talk about examples in which it's not so easy, not so straightforward to calculate the total number of outcomes, and or maybe not even easy to calculate the number of ways that that event could happen. So that's where the fundamental law of counting comes into play. Now, please understand there are two different ways this can be stated, and it really needs to be stated two different ways. The textbook states the fundamental law of counting in terms of events, because up here, the number of ways this event can occur, that's what this numerator is. It's about events. But notice that the denominator isn't about events, it's about outcomes. So I think it's important that the fundamental law of counting is also defined in terms of outcomes and trials. So your textbook, if you want it for events, look at your textbook. Here, the fundamental law is, in terms of trials and outcomes, if one trial has m different possible outcomes, m being some number, some integer, and another trial has n different possible outcomes, then when the two trials are considered together, then there will be m times n different possible outcomes. And I think it's important that we do an example, a real simple example of this to clarify it. Okay? The point is, we simply multiply the number of outcomes together. And please understand that the fundamental law of counting is always expressed in terms of two outcomes, two trials or two events, but that can be expanded to 3 or 4 or 5 or 50 or 100 or whatever is necessary depending upon the problem. So let's do an example, simple little example. Let's talk about food. Let's talk about eating, about a meal. Let's say we go to a restaurant and we find that we have 3 entree choices. We have chicken, I abbreviated these so they fit, chicken, steak, and spaghetti. Okay? Those are my 3 entrees. The vegetables to have to choose from are beans, salad, peas, or corn. The drink I have to choose from is Coke, milk, water, tea, or coffee. Those are my choices. Now, I want to make a meal. And my meal will consist of an entree, a vegetable, and a drink. All right? One example would be chicken with beans and a Coke, or chicken with beans and milk, or chicken and beans and coffee, or steak and salad and water, or spaghetti and corn and milk. As you can see, there's many, many different possibilities here. And that's exactly my question. My question is, how many different possible unique meals are there, choosing from 3 entrees, 4 vegetables, and 5 drinks? Well, you might think that's a very complicated problem, but it really isn't if you can just apply the fundamental law of counting. It says, given one trial of selecting an entree, that can happen, well, obviously 3 different ways. So we'll put a 3 in here. Our next trial is choosing a vegetable. And there are 4 different possible outcomes there. So we put a 4 here. Our drinks, there are 5 different possible outcomes. So we'll put a 5 here. And the fundamental law of counting says simply multiply these together. 3 times 4 times 5 is 60. And so that simply tells me that there are 60 different possible unique meals that we could come up with. It is that simple. Well, is it always that simple? No. We're going to have some complication, but that's the basic idea. So let's do another example. I randomly chose 8 letters, just at random. And here it is. Given these 8 letters, how many different ways can we select 3 of them? The 8 letters that I randomly chose were L-O-V-E-M-A-T-H. Yeah, I just came up with them just by random. Sure it is. So I want to know how many different ways I can select 3 of them. And so using the fundamental law of counting, we're going to make 3 blanks. One for selecting the first letter, for selecting the second, and for selecting the third. However, there are 2 basic questions that must be answered before we can do this. Because I can think of at least 3 different ways that I can interpret this question. I don't think interpretate's a real word. Question number 1 is, well, once I use a letter, can I use it again? Now, I got to tell you, when I present this problem and this question in class, there's always several students say that, no, you can't use it again. And I have to stop the class and tell them, you don't get to decide the answer to this question. We're just the mathematicians that are finding the answer. This is a question that either has to be obvious from the context of the problem or else has to be given by the person that is presenting this problem. We don't get to answer this. We have to know the answer to it, but it's not our choice to come up with the answer. We have to be told which one it is. Okay? So please understand that. Now, once again, the question is, once I use one of these letters, am I allowed to use it again? If the answer to that is yes, I can use it again, then we'll do the following.